So let's look at collectives and then non-blocking collectives. So if you have used MPI, you must have used collectives because they are, they're needed in programs. That the patterns that they represent are needed by the nature of your computation, and they provide better performance than what you could do by hand. So you could call MPI broadcast to broadcast data from one process to all others, and all these operations take a communicator argument. So by all other, when I say all others, it doesn't mean your entire job. It is whatever is the communicator you pass to that function. And there are ways to create smaller communicators representing smaller groups of processes. So the collective can happen across that. So MPI reduce does some kind of arithmetic operation and returns the result to a single process, and so forth. So the first collective function that doesn't do any communication is MPI Barrier. MPI Barrier is used more than it should be, I would say, because it is very often not needed in an application, and I'll get into that a little bit. The way it is defined is it is a synchronizing point. So MPI barrier is defined. What it says is that no process, when you call MPI barrier, no process can leave the barrier, can exit from the barrier until every other process has entered its barrier, right? So when a process exits its barrier, it can be sure that every other process in that communicator passed to that function has at least entered the barrier. It doesn't know whether they have they will of course exit in a few microseconds at most, because there's nothing to be done in the barrier. But this process doesn't know that. It knows that they've all entered the barrier. So that is a synchronization point. So, but the problem is that I see codes where people add an MPI barrier for no good reason, really. That is, yeah, go ahead.
What is the difference between MPI wait all and barrier?
Yeah, so MPI wait all is not a collective function, for one. So MPI wait all is used for completing non-blocking point-to-point communication, I sends and I receives. Suppose you have done 10 I sends and I receives to different processes, and you call MPI wait all. That's a local function just to complete those point-to-point communication operations. Others don't need to call that function. So the first definition of a collective function is that every process that is part of that communicator must call that function. So that is the definition of a collective function. So there are two concepts: collective, what is collective, and what is synchronizing. And I was going to get to that in a slide or so. But yeah, go ahead.
Is it a good practice to use MPI barrier if you're measuring the execution times of program?
Yeah, that's one use. I was just going to get to that. So one use, I think, yeah, that's the bullet at the bottom there. One use for MPI barrier is when you're timing how long it takes, how long your program takes. So typically, when you're timing a block of code, you would call, and you're doing a parallel program. You want to measure the time when all these processes are running that code at the same time in parallel. So you call MPI barrier to make sure that everyone has reached that stage in their program, and then you start the timer with MPI W time. You run whatever that code is. Then you again call MPI W time everywhere, and then you measure the difference between the end time and the start time, and then you calculate the maximum time taken by everybody or something. So that's one place where it makes sense, because you want to make sure that everybody has reached there and they have started at the same time and they're executing in parallel. But when you're not measuring time, you could comment out that barrier there, because it's not needed. What I find is sometimes barriers are just thrown in just to be sure, or just to be safe, or if I've done a lot of code, I'm doing a lot of stuff, let me just put a barrier here. No, you don't want to, you don't need to be safe. Because in MPI is a distributed memory programming model. Everyone's operating on their own data. You rarely need to synchronize with a barrier like this. If you're doing shared memory programming, where there is a shared, your processor is operating on a shared data set, and one process is writing and the other is reading the same data, there could be a race. You want that ordering to happen. There you might have you need some synchronization, be it barrier or whatever, because you need to enforce some ordering. In MPI, you don't need to enforce that. You typically don't need to enforce that order, so you can avoid. So one good thing to do is, if you're dealing with some application code, you can just search for, are there MPI barriers in that code? Don't just go and remove them. Look at it and say, why is this barrier there? Is it needed, or can it be commented out? Some people have even developed tools to go through source code and figure out, are there unnecessary barriers or necessary barriers. I will say that in the afternoon, after the one-sided communication, in the hands-on exercise, there is one case where you will need a barrier or some other form of synchronization, but that's where you're doing one-sided communication where one process may not know that the other has done something, and that's where you need a barrier. But in the regular collectives and point-to-point, each process generally knows where the other is. So try not to do that. And as I said, I wanted to talk about the difference between what is collective and what is synchronizing. So a collective function is not necessarily synchronizing. I'm not speaking about barriers here, in collectives in general. Collective means that everyone must call this function. All processes in that communicator, which is a parameter, they have to call this function in the right order. By that I mean, if you're doing an MPI broadcast and then MPI reduce, everyone must also call broadcast and reduce in that order. If somebody changes that will be an error. Synchronizing means that when one process leaves a function, exits a function, it knows the state of the other processes, whether they have entered their function, that function or not. Not all collectives are synchronizing, as we will see. Barrier was synchronizing, and a few others are, but not all. So for example, these functions are not synchronizing. So a broadcast sends data from root to everyone. A scatter sends the data from root to everyone, but not the whole data. It effectively chops the data and sends parts of the data to others. The gather is the opposite. It gathers data from everyone and sort of concatenates it and returns it to the root. The root can be anything, not just 0. It's another parameter. So the root could have been 3 or it could have been 2, whatever you specify there. So in these functions, they are collective but not synchronizing. So for example, when rank 0 does the broadcast, internally there's some algorithm that is used to do the broadcast. It could be a tree-like algorithm where the root sends to some process, and then now these two processes send, there's another tree, effectively internally a tree, and they send. So it takes log p, a logarithmic number of steps, and then everybody gets the data. The root may not even wait for the others to call the broadcast, because if you're broadcasting a small amount of data, maybe just one value, it's a small amount of data, it can be buffered on the other side. It will do its sense and exit the barrier. Whenever the others exit the broadcast, whenever the others reach their broadcast, they will get that data that was sent, and they will come out of their broadcast. So, of course, the other processes cannot leave the broadcast until the root reaches its broadcast, because they need the data from the root. But the root doesn't need those guys to call the broadcast. So the broadcast is often, is typically never, there's no synchronization. The root is done much earlier than the others. The others complete whenever they reach their broadcast and whenever they've gotten data from the root or from others in the tree. There's a the broadcast algorithm is implemented in a tree-like fashion. And similarly, in the scatter, the root will go and send the data to others. They will get it whenever they call their function. They don't even have to reach their function. And on the other side, the gather also, the senders will send their data. Only the root needs to wait to get the data. Is this part clear? That there is no synchronization here. Now, there are other functions that are both collective and synchronizing, and they're synchronizing because of their nature. That is, everyone needs some data that is contributed by everyone else. So that makes it synchronizing. That is, because you need data from everyone, you cannot get out until everyone has called that function. So that implicitly makes it synchronizing. So this is an MPI all gather. So these functions have an all in their name. So all gather does a gather operation, but instead of just the root getting the result, everyone gets the result. So now everyone needs data that is contributed by all others. So there is no option, but they end up waiting for everyone to call that function. That's so in MPI programs, there are implicit synchronization points anyway because of such functions, if your program calls such functions. So that's why you don't need a barrier. This is doing a barrier effectively. It's doing more than a barrier because it's doing this data movement, but there is a barrier like synchronization. Similarly, an all-to-all. So all-to-all is a generalization of all gather where everyone is sending data to others, but it's a unique data item. So it's not like this. There is a single A, B, C, D that goes to everybody. You have different amounts of data, different data that is going to different processes. So all-to-all is difficult to implement for an MPI implementation because there is a different data element going to each other process. So all these tree algorithms, they don't help so much. In the earlier case, since it's the same data going to everyone, you can create a tree and kind of fan it out. But here, these are more difficult. So you don't use an all-to-all unless you need to, unless you really have unique data going to everybody. Then there's also the reduce operations, which do some in addition to collective communication, they also do some arithmetic operation like a sum or a min or max or whatever you want to. So the reduce does the result and sends it to the root. So here, by A, B, C, D, I don't mean a concatenation. It's actually A plus B plus C plus D or whatever operation you have chosen there, and there are various versions. There's also a scan function where it's also called a parallel prefix, where in this case the result depends on the rank of the process. So rank 0 will just get A, rank 1 will get A times B, or it's an arithmetic operation which could be plus. So A plus B, rank C gets A plus B plus C and D. So it's called parallel prefix. There are some algorithms that rely on this kind of operation. So again, these are not synchronizing. These are just collective because not everyone needs everyone else's data. And then there are also what are known as the V version of the collectives. V stands for vector. So like gather V, whereas scatter V, all-to-all V. So when each process has a different amount of data to send to others, then you use the V version, and you pass a vector that has these different counts. So that is another generalization. Instead of MPI scatter means everyone's sending the same amount of data, or rather the root is distributing the same amount of data to everyone. MPI scatter V means you pass a vector specifying how much data each rank gets, and similarly for others. And then there is another generalization, which is they ran out of meaningful alphabets. So the W version is where you can even have different data types, and that's in the all-to-all. So as usual, MPI has lots of functions because it's intended to cover every possible case. You don't need to worry about all of them, though. Yeah.
So
Can you define the reduce on data types that are not the standard data types?
Yes, if you define your own reduction operation. So the basic reduction operations, like some will work on the basic types, but you can create your own functions, and I think I have a slide on that. And those functions can operate on the data type, because since you're defining the function, you need to know the data type also, and then it'll work that way. Yeah, so these are the built-in or the predefined reduction operations that you can select from. It's the usual min, max, sum, the logical, bitwise logical operations. You can do a bitwise or, bitwise and a whole bunch of them. You can even find the maximum and minimum locations of elements in an array and so forth. And as I said, you can create your own function if the predefined doesn't work for you, or if you want to do it on a derived data type, you can create your own function and register it with MPI. So that's the way you create an MPI reduction operation, and you have to specify whether the function is commutative or not. That is, whether the MPI implementation can assume that you can do A times B, or B times A, and the result is the same. And the reason is all these parallel algorithms, whether there are any restrictions on the ordering in which internally the operations get applied. So you have to specify that, and once you have passed this function, then MPI will use your user-supplied function to do the reduction operation. So that's a more complex use of the MPI, of the reduction operation. Any questions before we move on to non-blocking collectives? Yeah?
So in my algorithm, like if I have a collective which doesn't require the synchronization, that is like less expensive compared to like the one with synchronization.
Yes.
For example, all these iterative methods, they need all reduce.
They need all reduce, okay? Yeah. So that is synchronizing. So all reduce is synchronizing because it's a reduce that everyone gets the result from, right? So everyone is waiting to get the result. So that is synchronizing. But if you need it, you need it. I mean, there's no option there. Yeah.
So broadcast is also like a collective.
It is a collective. It is.
So in my case, I have to find some value equal to this, like if command, and then if it's in that value,
yeah,
then broadcast it to everybody.
Yeah.
I do not have to put a barrier for that.
No, no.
So if some node comes earlier and it doesn't have that if value, so it will wait at the broadcast until the value that should be broadcast by some other node.
Yes, they must. All nodes must call broadcast the same number of times. So if it's data dependent, that doesn't work. So I'm not understanding your case exactly, but the timing doesn't matter. When they call the broadcast doesn't matter, but it has to be called the same number of times.
So my question is, like, let's suppose if I have 100 nodes.
Yeah.
And suppose 99 node came to some command and it found that it doesn't need to call broadcast. So will it wait for broadcast to be done by 0th node when 0th node arrives at that?
But who's the root of the broadcast? Who's sending the data?
0 will send the broadcast to 99.
To everybody, you mean?
To everybody.
Yeah.
But 99 came to that point earlier than 0.
That's okay. The timing is okay. So if 0 calls the broadcast, but nobody else has yet called it, they may call it 5 minutes later or whatever. That's okay. But they must all call it the same number of times. So 0 cannot call it twice, and somebody else calls it 3 times and 4, because they will hang in those extra numbers. Because either the data gets buffered internally, or 0 will wait until they will call their broadcast, depending on the size of the data. If it's a very big broadcast, a huge amount of data, then 0 will wait until everybody calls their broadcast, because the communication won't happen internally. Not wait until everybody, but at least whom it needs to communicate with in that algorithm. But for small data, it will just send it and go ahead. They will get it whenever they reach there. So that's another example of barrier that you don't need. You can avoid that. So, yeah. Any other question? Yes?
For creating your own reduce function or operation, if I, for example, have a sorting function, so in my code to check for correctness, I just have to do kind of a distributed sort.
Yeah.
The reduction operation do, I don't know, pretty similar to, I don't know.
Yeah, I don't think you can do a sort in as a reduction operation. The reduction operation is more like a, it's a, like a sum or those kind. You cannot.
What about like, I don't know, I have a long string and I'm just stitching the strings together.
Maybe we can talk offline to understand exactly what you're doing. Yeah. Yes? Yeah.
So is it necessary that each thread would call broadcast, or is it at the process level that you?
Good question. So so in MPI, all this is defined at the process level. So if you have multiple threads, if they all call broadcast, say collectives, that means there are that many collectives taking place. So there have to be that many matching collectives on the other side. And there are additional constraints that I think Bill will cover later in the afternoon. That because if you're calling collectives from multiple threads, what is the order in which they execute? Because threads execute concurrently, and unless you manage the ordering in which these collectives are executed, it might result in one ordering on one process, another ordering on the other process. So that might be that'll be erroneous. So it is the user's responsibility to ensure that they get executed in the right order on all processes. That might require some inter-thread synchronization of your own to add. So if you're doing a broadcast from one thread and a reduce from another thread, you have to make sure that there is some ordering here so that on each process, the broadcast is called first and then the reduce gets called second, because there are no tags in the collectives. The collectives assume an order. The MPI point-to-point has a tag parameter, so you can match messages based on the tag. There is no tag in the collectives. Another option is to have only one thread to call the collective, and then this problem goes away. Yes?
So when you use all-to-all or all-to-all W with MPI derived types, does it split the derived type up?
No, it won't split the derived type. It's in unit of the type. So it's similar to a regular communication. So when you do an MPI send with a derived type, you don't send you don't split the type. You send it in count units of the type, right? So even all-to-all takes a count and data type parameter, which is in units of that type. Yes?
Is there an advantage of multiple threads doing the collective instead of one? Because
multiple threads?
Yeah.
There may not be. I mean, performance-wise.
If you're sending an array and
particularly with now that there are non-blocking collectives, you may not need to do that. It just adds complexity, particularly the ordering that becomes your responsibility to make sure that they are called in the right or same order on all nodes. It's probably not useful to call collectives on multiple threads. Whatever benefit you can gain from that, you could gain from using the non-blocking collectives, which I'm getting to. Okay, so the collectives that I talked about so far, they've been there since MPI 1 days, and they were defined to be blocking operations. What that means is a process does not exit the collective until its part of the operation is over. It doesn't mean that the operation is completed elsewhere. It is done with its job. It has either got the result that it needs, or it has sent the data that may be needed for others to get their result. So that's what is meant by blocking. MPI 3 has also defined non-blocking versions of all these collectives. So the same collectives, there are now versions that have an I before their name. So it's an MPI I broadcast, similar to I send, I receive, and MPI I reduced, I all reduce, and so forth. And they're defined in the same way as non-blocking communication. They return a request handle, and you do a test or wait or whatever to do the completion. And the idea here is that you can potentially overlap the collective communication operation with computation. And you can potentially avoid deadlocks, particularly if the multi-threaded case becomes a problem when you try to do collectives from multiple threads. Instead, you can do it from one thread and just follow the ordering and do it in a non-blocking fashion. So the semantics are simple. So this is the the usual non-blocking, as you know. You call MPI I send, you get a request, and you can either test for completion, which is a non-blocking test itself, or you block on the wait call, and these are various versions of on a single request or multiple requests. The collective operations are the same. They return the same MPI request. Now, what are the semantics of the collective? So one is that the function will return by no matter what means. It will not wait for somebody else to call an MPI broadcast. It will not depend on the state of other processes. It will return immediately. You cannot assume that anything has happened when that function returns because it's non-blocking. The operation is not completed at this time. You have to call the usual test and wait functions sometime later to know when the operation has locally completed. Again, the completion is always local. What are the restrictions? The restrictions are you need to call them in the same order again. So if you're doing an I-B cast and an I reduce on one, on others also you have to call them in the same order, I-B cast and I reduce. So it's the same as the blocking collectives. And the non-blocking collectives does not match a blocking collective on the other side. So if you're calling an I broadcast on one and just a regular blocking broadcast on the other, that doesn't match. So that would be an error. You have to call I-B cast everywhere. So it makes sense to have that kind of semantic. So the basic idea is it allows asynchronous progress. You can potentially overlap communication with computation. And there was some, so this came as part of MPI 3, which was about 3-4 years ago. And prior to that, there was some research work that showed the benefit, the need for these kinds of functions in real applications, and implementation that also showed that it can be implemented efficiently. There was a libnbc library by Torsten Hofler, which might still be available, but you can get it from MPI implementations in any case. So now that raises an interesting question that if there are all collectives have a non-blocking version, there is even a non-blocking barrier. There is an MPI I barrier, which is a non-blocking barrier. So what does it even mean to have a non-blocking barrier? So does anyone care to take a guess as what could what is a barrier? What is non-blocking? So what does it mean when you call an MPI I barrier and come out? What does it mean, and what does it mean when you call MPI test or wait? Yeah.
So maybe like I want to do a barrier, but I can do some work that's not related to the barrier, just for preparation. So. Right.
So it's effectively splitting the barrier into two phases, like a notify phase and then the wait phase. So when you call MPI I barrier, and you're not waiting for anybody to call their I barrier. You're just notifying the MPI implementation effectively that I have reached my barrier. I don't need to know if others have reached their barrier so far. I have some other work I can do in the meanwhile. It's only when I call the wait function for that I barrier, that's where I really need to know now that everyone else has reached their barrier, and this is effectively the MPI barrier. So it gets split into two parts. Again, it's a performance optimization that if you don't really need to wait, because barrier is blocking, you will not come out of it an MPI barrier until everyone reaches. So instead of wasting that time, if you can do some more work, you can say that okay, I'll call MPI I barrier. Everybody else must follow the same thing, and only when I really need to know, I call the wait. So this has been there in some other programming models. So the UPC, the Unified Parallel C, which you'll hear about on Thursday afternoon, has always had both a blocking and a non-blocking version of barrier. I think it was called UPC notify and wait in their version. So there are examples where it is useful. Yeah. So the processes they notify in a non-collective manner, but the synchronization happens collectively. So that effectively that wait is where the barrier semantics get applied. That you cannot come out of the wait until everybody has called their I barrier. You don't have to wait for them to call their wait, right? Is that clear?